Okay, got it.
Okay, because I already have monitor here.
Okay.
Okay. Rolling, stream, project, go, 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 go. Save.
Hi, my name is Dr. David Sokol, and I'm speaking to you on behalf of the Corona-Free Movement. Tonight's presentation is going to look at cell armor as a product to address COVID-19 infection. It's a combination nutraceutical that, let's start over. Okay. Hi, my name is Dr. David Sokol. I'm speaking to you on behalf of the Corona-Free Movement. We're going to look at a nutraceutical product that's available in the marketplace that combines humic acid with a peptide. The talk that we're going to have is tonight's talk is going to look at the anatomy of the COVID-19 virus and each of the ingredients that in combination give us cell armor. So let's first look at cell anatomy and the mechanism of infection with COVID-19. So when you look at the COVID virus, you're going to see red upside down or inverted pyramids speckling the entire virus. Those are spike proteins or S-glycoproteins, and that's going to be relevant across tonight's talk. So just track the idea of a spike protein or an S-glycoprotein and take note of it as we've done here. Here's a three-dimensional image of that same spike protein that was published by some Chinese researchers in February 2020. And this particular infographic of the COVID-19 virus illuminates three things that I need you to know. The S-glycoprotein, or spike protein, the genetic material inside the virus, in this case RNA, and then the binding site between the spike protein and the ACE2 receptor in this last illustration. When the COVID-19 virus binds onto the cell membrane, there's a series of responses. We're actually using the SARS 2002 virus to walk through that viral binding process because the SARS 2002 virus and COVID-19 are both coronaviruses and they both bind to the ACE2 receptor on the cell membrane wall. So using this particular infographic, you see the SARS virus binding to the ACE2 receptor. And once it does that, it's pulled into the cell, in which case the genetic material inside the virus, in this case RNA, is released into the cell. And if you move to the next slide on the presentation, you'll see that there's a series of genetic manipulations that occur with that viral DNA in order to take over, in this case, the host's cellular machinery so that we can manufacture additional virus. The details aren't important, but what is important to understand is that there is a genetic processing event which is ongoing in the cell solely for the purpose of replicating the virus and distributing it to more cells in the body during an infection. What is interesting and important to understand about COVID-19 using SARS 2002 as a comparison is the affinity of the COVID-19 virus for that ACE2 receptor. It's anywhere from 10 to 20 times more. It's anywhere from 10 to 20 times. The COVID-19 virus has a binding affinity that's 10 to 20 times stronger for the ACE2 receptor than the 2002 SARS virus. That may be an explanation, or at least part of an explanation, for why COVID-19 is as infectious as we're currently seeing. That may be an explanation for why COVID-19 is as robust as an infectious agent relative to the 2002 SARS. So let's review the mechanism of viral binding through the series of diagrams here. So you see a virus in the background with glycoproteins or spike proteins with pointed. So let's review what we're seeing. So let's review the viral binding mechanism using a series of illustrations. And in this particular illustration, you see a virus with spike proteins of different colors. The arrows are identifying those glycoproteins. And then you see an ACE2 receptor in a yellow circle on the bottom right of the screen. In this particular illustration, you see the virus approaching the ACE2 receptor. And then here, the S-glycoprotein is binding onto the ACE2 receptor. With that, you get a transformation or conformational change of that S-glycoprotein, which enables the cell and the virus to fuse. Now let's take a look at the first ingredient in cell armor, namely humic acid. What is it? What's its potential efficacy? Where does it come from? So humic acid was discovered in 1761 by Wallerius, and the first publications in the medical literature actually popped up about 25 years later, 1786. In 2020, humic acid is used predominantly in the industrial sector, mostly oil and gas as a lubricant, but there are also fertilizer or agricultural-based applications in terms of fertilizer. Humic acid is also traditionally used in Ayurvedic medicine, which is how it crossed our particular interest. This next slide, the intent here is to distinguish between humic acid and another humus, in this case the humus that is commonly seen in topsoil or above the topsoil. And the reason to share this is just to distinguish humic acid from humus. They're different. Humic acid is actually the byproduct of Humic acid is actually the byproduct of decomposed organic. Humic acid is actually the byproduct of decomposing organic materials from the Paleozoic coal age about 280 million years ago. In combination with water, heat, and microbes, the dead vegetation was chemically. So the origin of humic acid. The origin of humic acid comes from decomposed organic material from the Paleozoic area about 280 million years ago. When you combine plant material with water, soil microbes, and time, humic acid is the result. And you see these deposits around the world. And humic acid is the humic acid is derived from, humic acid comes from dead plants. But in this case, the plants died about 280 million years ago during the Paleozoic era. When you combine dead plant material with water, soil microbes, and time, humic acid is the result. As you can see from the picture on the right here, humic acid has to be mined, which is also a distinguishing feature. As you can see from the picture on the right, humic acid has to be mined. What that means is that sourcing is very important, because when sourced appropriately and processed appropriately, humic acid has actually been shown to inhibit viral fusion, which is relevant to the conversation with COVID-19. The following is a three-dimensional model of humic acid that has been used in cell armor. And this The following is a molecular model of humic acid that's been used in cell armor. This particular animation shows the three-dimensional structure and gives some insight into the potential binding sites of humic acid with its virus target. All right, so let's review the antiviral activity of humic acid. And we can start by looking at a variety of institutions that have assessed this particular activity. In this case, the University of Southern California, Southern Research Institute, Specialty Laboratory, and the National Institute of Health. Although each of these organizations reviewed different parts of this antiviral spectrum, the take-home from reviewing the literature is that humic acid is a very effective antiviral in terms of HIV, herpes simplex, cytomegalovirus, Epstein-Barr virus, and hemorrhagic fevers. If we dig into the literature specifically from the NIH, we have an opportunity to calibrate the potency of humic acid relative to prescription medications that are considered computer just blew up. Okay. If we focus on the NIH studies, we have an opportunity to calibrate the strength of humic acid relative to other standards of care in the antiviral space. The focal point of the conversation is going to be looking at the IC50 and the IC90. IC50 is simply a way of understanding what concentration of humic acid is required to inhibit 50% of the viral activity. The IC90 is the same idea applied to 90% of viral activity. So when we look at the first table on the left, table 3, you see you're able to make a comparison between humic acid in red and acyclovir in blue. And we'll follow that model when we're reviewing all of the NIH data in the following slides. But what you can see in this particular table is that the humic acid is less effective than the acyclovir as an antiviral. But what's notable is that it has antiviral activity, meaning that the acyclovir, the standard of care for this particular study, was effective, but the humic acid was almost as effective. If you move to table 4 and you look at herpes simplex type 2, you see the opposite effect, where in this case, humic acid in red, acyclovir in blue, the humic acid was more effective at an If you look at table 4 on the right, and herpes simplex, if you look at herpes simplex type 2 in the table on the right, you can see that if you look at table 4 on the right and you compare humic acid in red to acyclovir in blue, you can see that humic acid is actually more effective with an IC90 than is acyclovir in this particular example. Moving forward to tables 6 and 7, looking at both varicella zoster or chickenpox on the left. If we move to the next slide and look at tables 6 and 8, we can compare the effectiveness of humic acid with varicella zoster virus, which causes chickenpox and shingles, as well as Epstein-Barr virus, which can cause mono. In both of these instances, humic acid has efficacy or effectiveness, but the effectiveness is not comparable to what we were seeing for the herpes viruses. Now, if we look at the influenza viruses as a group, and that means we look at H1N1, H3N2, we can calibrate the effectiveness of humic acid against the influenza virus. And you see from these particular tables that there is a comparable efficacy between the standard of care in this study, ribavirin, and humic acid that's dependent on the type of influenza virus that's being assessed. So let's look at a clinical trial that included humic acid and influenza virus. But before we do that, let's look at some treatments. Let's look at a clinical study. Hold on. So let's look at some clinical trials that examine humic acid. So let's take a look at some clinical trials. But before we do, let's look at some developments in the COVID-19 space. And this particular slide gives us some visibility to that. Now, it's important to understand that there are no FDA-approved treatments for COVID-19 as of today's date. There are several products that are in development. Remdesivir from Gilead Sciences is one of those. It's an anti-Ebola antiviral that's being looked at as a potential treatment. Kaletra, which is an anti-HIV antiviral, was being examined recently, but the most recent reports that I've reviewed have shown that on a standalone basis, it's not as effective as had been hoped, but perhaps in combination with chloroquine, an anti-malarial, there may be some efficacy against COVID-19. Monoclonal antibodies are also being examined, and of course, organizations and companies around the world are looking for a potential vaccine. Regardless of the scenario, the development timeline is anywhere from 4 months to 12. So let's look at that clinical study So let's look at a clinical study that looks at the efficacy or effectiveness of humic acid against influenza. And in this particular case, we're looking at a randomized, double-blind, placebo-controlled study. And that gives us an opportunity to assess at a higher level the effectiveness of humic acid, in this case against the influenza virus. The way this study was designed, it looked at the anti-inflammatory and the antiviral properties of humic acid. We also know from the literature that it has antibacterial activity, and we also know that it's safe in doses up to 100 milligrams per kilogram. This particular study cited 50 milligrams per kilogram. So just as a review, what does humic acid do in the situation when it's exposed to a virus? Well, the primary activity is that it's going to inhibit viral fusion. There is a secondary activity which has to do, there is a secondary activity where humic acid interferes with the RNA polymerase and the genetic processing associated with the infection. There is also a secondary activity where humic acid inhibits the endonuclease of... So before we go into the details of the study, let's at least review what humic acid does. And on a primary basis, it's important to remember that humic acid inhibits viral fusion with the cell membrane. There are secondary activities as identified in this slide, but So before we review the ideas behind the study, let's take a look, or let's review the activities of humic acid relative to... Before we look at the study details, let's review what humic acid does. The primary activity is it inhibits or it blocks viral fusion with the cell membrane. That's the most important take-home to remember and hold on to during this talk. Secondary activities, such as what's described below, that humic acid inhibits viral RNA synthesis, is relevant, but functionally it's more important to understand that humic acid blocks viral fusion. The behavior of humic acid, or the behavior of a virus when it has an opportunity to choose between humic acid and the cell membrane, is given a choice, viruses are going to choose humic acid over. In this particular study, one of the things that we learned is that given the choice, the influenza virus will choose humic acid over the cell membrane. Very interesting and unexpected finding, but what that essentially says to us is that the affinity of the virus for humic acid is much stronger. Oh, all right. Okay.
Start from the last part.
Okay. Okay. All right. Ready?
Yeah.
Okay. One of the important findings from this particular study is that given the choice, the influenza virus is going to preferentially bind to humic acid versus the cell membrane receptor. The other surprise finding is that the affinity of humic acid for the influenza virus is so high that the influenza virus will actually leave the bound cell membrane and move to humic acid. So how is this study designed? So there were originally 40 patients that were enrolled in the study. 37 completed the study. Those who left. So how was this study designed? There were 40 participants initially. 3 dropped out during the study interval, so 37 completed the study window. The study was completed over a 2-week window. Okay. So how was this study designed? Ultimately, 37 participants out of 40 completed the study. During the study, individuals were divided into 2 groups, a treatment group and a placebo group. Those in the treatment group received 500 milligrams of humic acid 3 times a day. Those in the placebo group received something. So how was this study designed? Ultimately, the study evaluated 37 individuals. Okay. So how was this study designed? Ultimately, let me think this. All right. So because this is a randomized, double-blind, placebo-controlled trial, okay, we had 2 groups of individuals. Some received humic acid. Some received a placebo that looked as though they were receiving humic acid. In the end, 37 patients completed the study. Regardless of what treatment group individuals were in, they all received 500 milligrams of a product. They were instructed to take it 3 times a day for 14 days. Participants were evaluated at baseline, day 7, and day 14. Okay? And the things that the researchers were looking at were questions and the things that research, and the things that was that a phone?
You set over
Oh, okay.
4, 3, 2, 1.
And the things the researchers were looking for, and the endpoints the researchers were following included subjective impressions, blood test results, and vitals. In terms of subjective impressions, what were they following? They were looking at in terms of symptomatic endpoints, the assessors were looking at fever, muscle aches and joint aches, headache, fatigue, nasal congestion, ear pain, and cough. The biomarkers that were followed included looking at white blood cell counts and complete blood counts, immune system markers like CD4 and CD8 cells, inflammatory markers like tumor necrosis factor alpha and interleukin 8, and then typical serum chemistries and liver enzymes. prior to subjects coming in for an assessment on day 7 or day 14, the only restriction on them was that they shouldn't take any medication that would have an impact on their fever. So what are the results? So subjectively, what we see here in the table at the right is the humic acid group in the middle column and the placebo group on the far right. And as you scan these numbers, whether it be cough or fever or even muscle aches and joint aches, myalgia and arthralgia, you see a notable increased improvement in the humic acid group versus the placebo group. 61.9%. So if we take a look at some subjective results, what we notice here is that there was a greater reduction in symptoms across the humic acid group relative to placebo. And as you scan the information in the table, whether it be cough or fever, muscle aches and joint aches, or even chills, the numbers are notably different for those in the treatment group, the humic acid group, versus placebo. And although these results are not statistically significant within the group, there is significance between the groups, which is why we've included this information here. Okay. All right, if we look at a performance index called the visual analog scale, you see a significant difference between the humic acid group and the placebo group in terms of their ability to complete activities of daily living, including going to work. And perhaps most notably in this particular table is if you look at the 40 to 60-year-old group, 164, and most notably, if you look at the 40 to 60-year-old subgroup, the humic acid group saw 164% improvement relative to 70.3% improvement in the placebo group in terms of how they felt or how capable they were to complete activities of daily living, including going to work. When we talk inflammation, let's look at tumor necrosis factor alpha. If you understand nothing about if you want to talk about inflammation, let's look at tumor necrosis factor alpha and then interleukin 8. And the take-home message from this particular slide is that in the humic acid group, you saw a substantial suppression of inflammatory drive in the presence of humic acid. The other thing you see with interleukin 8 is a more subtle suppression of interleukin 8 activity. That's relevant in an infectious model because less interleukin 8 suppression means you have a more robust immune response. So suppression of TNF alpha is a good thing. Mild suppression of interleukin 8. So in summary, a more notable suppression of TNF alpha is a good thing. A more subtle suppression of interleukin 8. Let's do that. So let's look at inflammation, humic acid, and influenza. This particular slide looks at tumor necrosis factor on the left and interleukin 8 on the right. What we see on the left is that there's a significant suppression of inflammatory drive or inflammation in the presence of humic acid, whereas on the right we see that there's a less suppression of interleukin 8 in the presence of humic acid than in the presence of placebo. Interleukin 8 is notable simply because we want less suppression in this instance than more, which is what we were after with tumor necrosis factor alpha. And the reason that we're interested in that is that interleukin 8 actually promotes an immune response, whereas tumor necrosis factor alpha is a marker of inflammation associated with infection or some other painful stimulus. If we move to the next slide and we look at immune cell markers, CD4 and CD8, in this case you see an increase in immune cell numbers in the humic acid group and a decrease in cell numbers in the placebo. The net change between both groups relative to CD4 and CD8, 6%. So what kind of adverse events were noted here? Most notably, gastrointestinal symptoms such as diarrhea, stomach aches, and whatnot. There were also some changes in liver function tests. The assessors in this case opined or decided that this was related to alcohol. So in this particular table, we have a chance to see what kind of side effects were associated with the use of humic acid. And as you can see on the table on the right, so in this next slide, we have an opportunity to look at the side effects associated with the use of humic acid. And if you look at the table on the right, you can see that most of the side effects had to do with the gastrointestinal system, or the gut. Diarrhea and stomach discomfort were the most common complaints. The researchers also saw some change in liver function tests in a few of the study participants. They were not able to establish what the cause of that was, although they opined, meaning they guessed, that alcohol may have been a contributing factor. So let's move away from the humic acid side of cell armor, and now let's look at the peptide side of the equation. But before we do specifically to cell armor, let's at least learn a little bit about what a peptide is and how it may be applied in clinical medicine today. So what is a peptide? Typically, it's a sequence of 2 or more amino acids. And a peptide is by definition between 2 and 50 amino acids in length. Anything more than 50, and we tend to move into a space which is... So what's a peptide? A peptide is 2 or more amino acids that have been linked together. By definition, peptides are between 2 and 50 amino acids in length. Any more than that, an amino acid is going to be reclassified as a protein. This infographic gives you an opportunity to understand amino acids on the far left as the building blocks of protein. When they're joined, they form peptides in the middle. And as the number of amino acids increases, you can move into the protein space on the far right. This particular slide simply gives you an opportunity to visualize the different amino acids. The take-home message that I want you to have is that peptides drive biology. They provide a The take-home message I want you to understand about peptides is that they drive a cellular response. Okay. So the take-home message that I want you to understand about peptides is that they drive a change in cellular behavior. And perhaps one of the best peptides to consider, or the one that's most familiar, is going to be insulin. Insulin is really 2 peptides that have been bound. One of those peptides is a 21 amino acid chain, and you can see that here in blue. And the other peptide is a 30 amino acid chain, and you can see that in the illustration here in green. Another peptide in this case is growth hormone. Growth hormone has 191 amino acids, so it's quite frankly, it's a protein. And it's also regarded as a hormone. Peptides that may be available over the market, at least in the United States, include glutathione, which is a 3 amino acid sequence, and then BPC-157, which is a pentadecapeptide, which means that it has 15 amino acids in sequence. In both instances, these peptides are naturally occurring. Other peptides that are available in the therapeutic space include cerebrolysin and dihexa to improve brain health, the thymosins to improve immune system function, cosmeceutical peptides that support collagen synthesis, and then there are bioregulators such as epitalin. This slide is simply present to offer you proof of concept that in the presence of a peptide, we see an inhibition of cell-to-cell fusion as well as an inhibition of infection. Those, you can track that by looking at the blue and red lines on each graph. The following molecular model includes humic acid with a peptide chain on the far right. So in terms of cell armor, what are we talking about on the peptide side of the equation? The peptide in cell armor is a 14 amino acid chain. We know based on in vitro testing that it binds onto the S-glycoprotein of viral membranes. And in this case, the peptide locks humic acid into place so that it doesn't have the opportunity. And in this case, the peptide locks humic acid into place. What do we see in terms of effectiveness when we combine humic acid with the peptide? You see 100% virus death with herpes simplex virus by day 3, 60% of... So what do we see in terms of... What do we see in the laboratory when we... What do we see in the laboratory when we combine humic acid with a peptide? As illustrated here, against HSV1, 100% virus death by day 3. For HSV2, 60%. When we're looking at viral binding inhibition, cytomegalovirus, 100% by day 3. Respiratory syncytial virus, 100% by day 3. And just to review the mechanisms of action, humic acid encapsulates the virus and prevents it from binding onto the ACE2 receptor if it were. So in terms of mechanisms of action, humic acid encapsulates a virus. So let's review mechanism of action. Humic acid binds onto a virus and prevents it. So let's review mechanisms of action. Humic acid encapsulates a virus and prevents it from binding. The peptide binds to the S-glycoprotein and locks humic acid into place. And what's particularly interesting is that the humic acid peptide combination seems to be indifferent to viral mutations or antigenic shift. So what are we seeing in the real world when we combine humic acid with peptide in the form of cell armor? And we can use a case example from Singapore. But first, it's important to note that over 285,000 doses of cell armor have been distributed in China, Hong Kong, Singapore, and South Korea. So if we look at one case example of a family of 6, we can use that, for guidance. And in this particular case, a family of 6 between the ages of 20 and 54 was hospitalized in Singapore after they tested positive for coronavirus in Singapore. The standard of practice in Singapore is to transport a family by ambulance to the hospital, and the criteria for discharge from the hospital include 2 coronavirus tests within 24 hours of each other. And the criteria for discharge in Singapore include 2 coronavirus assays 24 hours apart from each other that are both negative. For those that were hospitalized in this particular example, each participant took 2 cell armor tablets 3 times a day for a total of 6 tablets each day. The follow-up assay 24 hours after admission to the hospital in each case was negative. The follow-up assay 24 hours later in each of these cases was also negative. So the total duration of hospital stay for the members of this family was 3 days each. So how would you use cell armor? If you're worried about or you want to prevent yourself from getting an infection, take 1 to 2 tablets or capsules daily. If you're suspicious that you have an infection or you know that you have an infection, Then take 2 to 3 tablets or capsules 3 times a day. Thank you very much.